Hello once again, AP Calculus AB students, Mr. Record here, and we are actually recording live my Period 7 class. Can everybody get a hand for calculus? There we go. All right, that's the kind of enthusiasm I want to hear. Good. We're talking about section 7.1 in the Larson 9th edition textbook, area between two curves. And no doubt up until this point, you guys have probably done a lot of work with area, finding the area under a curve bounded by the x-axis. Well, things are going to change now because what I've got here is it says, with a slight modification, we can change the concept of finding the area of a region under a curve to finding the area between two curves. That deserves an ooh right there, doesn't it? Ooh, all right. So what we're going to do is consider the following graphs. And the way that I've got this little presentation here set up is probably better that we look at this middle one first. You know, in other words, if we were going to be finding the area here under the graph of F, right, which I call the region under F, obviously, if we're going to do so on the interval 2 to 4, we would just integrate the function f of x from 2 to 4, and then boom, everything is taken care of, right? That would give us the area that lies between the curve and the x-axis. Okay, now on the other hand, look at number 2 here. If we were to focus on the area that would lie below the graph of g, still on this interval 2 to 4, we would obviously integrate g from 2 to 4, and that would give us the area bounded by the x-axis. Notice in both cases, we are bound to the x-axis. But if we wanted this area here, though, in figure 3, what lies between the curves, doesn't it just make common sense to us all that we would subtract this region number 1 minus this region number 2, and that would leave us with this region number 3. So in a way, you can just say that you would subtract those two separate intervals. But rather than integrating twice, which is kind of silly, right? We don't have to integrate twice. We could go ahead, and since these two integrals have the same boundary, we could think of it as a subtraction problem first, and then integrate between the two boundaries, 2 and 4. Does that make sense? So really, you've got this grand equation or expression, I guess, that says if f and g are continuous on an interval, and this is really important, I can't emphasize this enough, the g function must always be less or equal to the f function. Right? A lot of times I like to kind of twist this around and say that the f function would be always above or equal to the g function. On some interval between a and b, then the area of the region bounded by those two graphs between the vertical lines x equal a and x equal b would be given by this expression here. Subtract your functions, top minus bottom, and then integrate, plug in your boundaries. Okay, very simple. So our first example, finding the area of a region between the two curves. And the curves in this case are y equal x squared plus 2 and y equaling negative x. Well, let's let y equal x squared plus 2 be graphed here in blue. And notice that the directions do say to sketch the graph, shade the region. So what we'll want to do is, let's say that this is a calculator inactive question, so put those calculators away, kids. Y equal x squared plus 2, we could go ahead and sketch this probably with a t-chart, right? This t-chart we could do in our heads. I don't think there's any reason for you guys to draw out some sophisticated chart. You guys are calculus students, for crying out loud. So let x equal 0, what would the y value be? 2. If x is 1, y would be 3. If x is 2, we are out of room, aren't we? Oh, let's go to this other side. Let's let x be negative 1. If negative 1 is squared, we add 2, we were going to get right back to 3, isn't it? So if we connect those 3 dots with what we know is going to be a parabola, right? This has that parabolic form to it. That would be our sketch. All right, let's use a different color, and we'll sketch y equal negative x. Well, y equal negative x is just simply a line that has a y-intercept of 0 that would also have a slope of, anybody? Negative 1, good, good. So maybe it would look something like this, right? And then If we look at this and think, well, wait a minute, that doesn't create some kind of bounded region, right? We don't have a bounded region yet. If we were to put our little cattle, right, our little cattle inside of this area, they would roam free, right? They could go over here and escape. They could go over here and escape. And that's bad. That's bad. So let's get rid of the cattle here. We need to create some other fences, don't we? So how do we do that? How do we create some more fences? Well, we continue to look at the rest of the problem. And we do have a couple of more curves, in this case lines, that we need to sketch. X equaling 0 is just the y-axis, right? It's the vertical line where all x values are 0. X equal 1, well, that would look a little something like this, wouldn't it? And now we do have an enclosed region. And it's a little unusual in that it's sort of lying partly above the x-axis and partly below. And that's new for us. We haven't seen that, especially those of you who are using the Larson textbook. Okay? And it did ask us to sketch the region, so let's see if I can come up with a clever way to do that. Maybe this would work. I'll shade the region. Yeah, there we go. Perfect. Nice. This highlighted yellow region, it's a little difficult to stay in the lines. Right. I wasn't much good at that in kindergarten either. So there we go. So we are now faced with setting up an integral that's going to do this job for us, right? This area of the yellow region. So if we recall our formula, right? And if you remember, our formula looks like that. We have the function f of x subtract g of x integrated from a to b. Now, which function is your f of x? That's going to be very important. If you look at the shaded region, we have a curve that lies above. It's always bigger. He is your f of x. The curve that lies below is your g of x. So your area would be the integration along the boundaries. Now, the boundaries would be, let's see, that would be a 0, would it not? And that would be a 1. So our boundaries would go from 0 to 1. They must be x values since we are going to integrate with respect to x. And then we would have our function x squared plus 2. Subtract our function negative x. And be really careful, you're going to subtract a negative x here. Okay? We okay? Any questions so far? Okay, now we'll simplify a little bit. Combine some like terms, get rid of some extraneous minus signs and parentheses. You could write it in descending order, but to be honest with you, it doesn't make any difference if you do that or not. Basically, the double negative will be taken care of in this step and really nothing else. Integrating, you're going to find out that some of the integration that you would do in simple area problems is going to be some of the simplest integrating that you've ever done. Right? Usually it's polynomial type of things. So integrating x squared, of course, is x cubed over 3. Integrating 2 would be 2x. Integrating x would be x squared over 2. And then don't forget we have the boundaries 0 and 1 to contend with, right? No plus c is needed in a definite integration problem. Right? And it's very fortunate that one of our boundaries is 0. That's going to make things really simple for us. Let's plug in a 1. We would get 1 cubed over 3, which is 1/3. 2 times 1 is 2, plus 1 squared over 2 is 1/2. And when it comes time to plug in a 0, we're going to get 0 in all 3 spots, right? So if we simplify this, scroll down a little bit, simplifying this, getting a common denominator of 6, I have 2/6 plus 12/6 plus, what would that be, 3/6, which is 12, 13, 14, 15, 16, 17/6. Or I suppose you could say 2 and 5/6 would be the same, 2 and 5/6. And when it comes to checking this, I suppose you could look and say, hey, you do have 2 full blocks here. Maybe this half block and that extra little portion could constitute a 5/6 of a block. And I think we've got a reasonable answer. While I'm still recording here, I think it's kind of worth mentioning that a graphing calculator has some limitations when it comes to doing a problem. Let me see if I can illustrate that here. I'm using the TI-Nspire CAS, CX CAS here, but just about any other graphing calculator should give you the same results. Let's go ahead and sketch these two guys. What was that first equation again? X squared plus 2, thank you, x squared plus 2. So we've got him, and then we'll join him up with the other graph, which was negative x, negative x. Okay. Now, let me move these names out of the way just a little bit. That's not good. That's never a good thing. That's always bad. Tell you what, let's just go ahead and sketch him again. Let's get graph 2 out of there. Okay. I apologize for wasting your time here. Okay. Maybe I better not touch him after all, huh? There. Okay. If we were to take a good look at trying to perform the integration here, and on the TI-Nspire, we've always been able to do that by hitting Menu, Option 6, Analyze Graph, and hitting Integral. Now, we have to state which particular graph we want to find the area under. So that's our limitation here. We'll choose F1 first of all, and then immediately it asks us to find boundaries. Well, in this particular problem, I think our boundaries were 0 and 1, right? So the best way to do that is to make sure that your pointer is along the x-axis, and once it kind of locks into a position, it'll let you know, in this case, the intersection point of the line and the axis happens to be at 0, 0. And then for my upper bound, I'll just slide this over till it says point on, and then boom, I've got my upper bound of 1. Now the problem is, as you can tell, this just computed the area underneath the parabola and above the x-axis. That's not quite the full area that we wanted, is it? So to sort of fix that, you would go through the process again. You would hit Menu, Analyze Graph, and use Integral once more. But when it asks for graph this time, we'll choose graph 2. And for our lower bound, we'll stick with our 0 and our 1. And you'll see that it does a pretty good job now of depicting that full shaded region. And I'm going to drag this result up here. And it's kind of interesting to note that the calculator thinks that this area right here was negative. But see, we know that's not true, right? That's not a negative space. It sure lies below the x-axis. But when it comes to actually finding the area, we need to treat that as positive. Right? There's a big difference between the answer to the integral being negative and what the actual value of the area is. Okay? In fact, if you do this the right way in finding the area, your f of x function would be 0. Right? It would be the graph of y equals 0. Take 0 minus negative x and integrate that, you won't get a negative 0.5. You would get a positive 0.5. Does that make sense? Hopefully. So you got to think about this as being a positive 0.5. Now, if you were to add these together, what's 2 1/3 plus 1/2? Yeah, this would be, what is that, 7/3 plus 1/2. That's the common denominator of 6. We would have 14 plus 3. Oh, what do you know? 17/6. It's the exact same answer that we had previous. Okay. So what we've got is both a graphic depiction of this particular area using the TI-Nspire, or sort of by pencil and paper method using the calculus. So hopefully this helps out. If you prefer, you can stick around and watch some of the other videos that pertain to section 7.1. See you next time.